Okay, so first, let's recall the theorem we mentioned last time. We call it the Big Theorem. This time, we give it a name. Called the Intercept Theorem. Okay. The intercept. Have you seen this word before? Amy, have you? The intercept.
Yeah.
Okay, so when we have this line equations, this will be the x-intercept. The y-intercept is when the intersection is about the following. So we have a triangle. A, B, C. So first we assume we have line that intersect the two sides at E and F. If we know that the two lines are parallel, suppose AB and AC at 2 points. If okay, if the two lines are parallel, then the corresponding sides of the two triangles have the same ratio. Okay, so we call this the intercept theorem. Last time we referred to the big theorem. Hope you have an impression of this, and we used several times to prove all kinds of similarity results. So this time we give the official name, the intercept theorem. If this line is parallel to the third side, then the corresponding sides of these two triangles have the same ratio. And the converse is also true. That's the first part. Conversely, if we have the ratio, okay, suppose now we don't assume the lines are parallel. We assume the ratios are the same. So this will be a number. Let's call this number R. Okay, so this is the intercept theorem and the converse. If we know the two sides are parallel, then the corresponding sides have the same ratio. Conversely, if we know the two sides they have the same ratio, then this line must be parallel to the third side, and they also have the same ratio as the previous two. A particular case is what we proved for the midpoint theorem. If E is the midpoint, we draw a parallel line, the F is also the midpoint, and the EF is half of BC. Okay. Special case, okay. So if we replace this by 1/2, then this is also 1/2. It's parallel and it's half of this. If we know this is parallel and the ratio is 1/2, then this is 1/2, this is 1/2 of this. And in our homework, you did the case when R is 1/3 and 2/3. Two-thirds. And you proved that if this is the 1/3 point, we draw a parallel line, then this will be 1/3 point of AC. And EF is 1/3 of BC. Also, you checked if this is 2/3, we draw a parallel line, then this is also 2/3 of AC. This will be 2/3 of BC. So that's what you had for the homework. So this intercept theorem is a big generalization of these two special cases. If the ratio is 1/2, we go back to the midpoint theorem. 1/3 and 2/3, that will be our homework. Okay. So from there, we introduce the similarity property. Two triangles. A, B, C. Okay, we call them similar. If the following conditions hold. This is the definition. of two triangles are similar. If they are similar, we have the following conditions. We have to check the following. Corresponding angles, same measure. Corresponding sides, same ratio. If we verify these two collection of conditions, then we see the two triangles are similar. If you search this online, you check some books, the order of the two theorems is very important. We cannot use similarity theorems to prove the intercept theorem because intercept theorem comes earlier than this, and all of our similarity theorems is based on the intercept theorem. Okay, so that's the key point we will use. The intercept theorem to derive. Because of this, we cannot use Okay, so get the logic straight. We will use the intercept theorem to prove similarity theorems, but not the other way. Okay, so now we may ask ourselves, do we have a proof of this theorem? We have proved a few special cases. We proved that when R is 1/2, the midpoint theorem. When R is 1/3 or 2/3, in our homework, we use congruent triangles and parallelograms. The properties of these two to establish this homework problem. And we can generalize this to all rational numbers. If this is a rational number, the same argument works. We can use congruent triangles, parallelograms, to prove the intercept theorem for rational ratios. But if the ratio is irrational, we have to use approximation. Okay, so a few remarks about tools for this are congruent triangles. The same method can be used to prove all rational cases. So when the ratio is irrational, we use approximation. Okay, so this is not a proof of the intercept theorem, but a guideline that how to prove it using the method, the congruent triangles and parallelograms. So theoretically, this can be done, but it require a lot of steps. That's why we skip it. Okay, so in the following, we will use the intercept theorem, even though we only proved a few special cases. Okay, so the first theorem is a direct application of the intercept theorem. Now let's reformulate. That A, B, C. I draw a parallel line that intersect at E and F. Okay. So the conditions are E, F parallel to BC. Then the two triangles A, E, F, A, B, C are similar. Okay, let's see how do we convince ourselves, how do we explain this? Why the two triangles must be similar? What theorem do we have? Keep in mind, we haven't established any of the similarity result yet. We only have the definition and the intercept theorem. Let's check to see that the two triangles are similar. We need to check the corresponding angles, same measures, corresponding sides, same ratios. Okay, let's check this angle condition. Are the corresponding angles have same measures and y? Okay, check angles. Amy, for this triangle, what are the three angles?
Angle. Yeah, those three angles.
So 1, 2, 3. Okay. So for the first triangle, we have 1, 2, 3. For the second triangle, we have angle Y the same as angle A, B and C. Angle Y equals angle A because the same angle. Angle 2 and angle B. Okay, Isabel, these two angles, do they have the
Oh,
same measure?
they have the same measure.
Why?
Oh, I think that's called corresponding angles.
Okay. Because the two lines are parallel and they are the corresponding angles of the parallel lines. Nice. Corresponding angles. Now angle 3, angle C. Aaron, these two angles, do they have the same measure?
Yes, they're also corresponding angles.
Also, yes. Also corresponding angles.
Or at least on the same line.
Corresponding angles of the same pair of lines. Okay, so now we checked the angles condition for similar triangles. We move to the side condition of the triangles. Second, we check sides. AE over AB, AF over AC, EF over BC. Are these three ratios the same? And why? What theorem guarantees this? The only assumption we have is the two lines are parallel. Is this enough? Kira, any thoughts? AE, AB, AF, AC, EF, BC.
I think the relation, like the ratio is equal.
Okay, so they should be the same.
Mm-hmm.
And the reason is our intercept theorem. If the two lines are parallel, the corresponding sides have the same ratio. Okay, so this is by the intercept theorem. Okay, now we have verified both the angles condition and the size condition for similar triangles. Therefore, the two triangles are similar. Okay, so at the very beginning, we don't use any of the similarities theorems. We only have the intercept theorem. And that's enough. We can prove the two triangles are similar. Okay, now let's go back to the definition. In this definition, we have two collection of conditions. We want to reduce the process to verify this. We claim this condition alone is sufficient for the two triangles to be similar. This is our first theorem about similar triangles. So this is an example of similar triangles. Now we go to the theorem of similar triangles. Given two triangles, if we can check the angles condition, then it's sufficient to claim, to conclude the two triangles similar. All right, how do we prove this?
A similarity theorem.
Okay, so at this moment, we cannot use that theorem yet because that theorem is based on this theorem. Okay, so now we can see the order of the theorems matters. So we have the intercept theorem, we have the definition, we have some examples, but we cannot use the theorem in the future to prove this theorem because that theorem, the AA similarity theorem, is based on this one. Aaron, is this logic clear?
Well, yeah, very mostly, yes.
Okay, so the reason we cannot use AA similarity theorem is that theorem is based on this one. Okay, like if this will be the first flaw. The AA theorem will be the second flaw. ASA will be the second flaw, third flaw. We go from the basement, the first flaw, the second flaw. We cannot jump to second flaw, then back to first flaw. We have to go this step by step. Okay. So to prove this, because these two angles have the same measures, we can make a copy of this triangle over there. So we make a copy. Since angle A equals angle E, we can find F on AB with E F can find GRAC with AG EG. Okay, so this can always be done. We can find a point such that they have the same length. Find a point such that they have the same length. So we found the 2 points. Next, we will connect the 2 points. Okay, so this mark stay there. Let me close it and reopen it. Okay, so now we connect 2 points. Oops, let's keep going. Okay, something is wrong with this. Let's compare the 2 triangles. The one we had before. Okay. What can we say about these 2 triangles? Amy, what do you say?
Um,
Are they congruent?
yeah.
Okay, how do how do you check this?
You could use the wait, no.
Ah,
ASA, I think.
okay, if you say ASA, so what's the first pair of angles?
The F and G.
F, angle G, that's what you said?
Yeah.
Why are these 2 angles have the same measure? We don't know. Okay, so what do we know? We know these 2 angles are the same. And we know the 2 sides,
Yeah, you can use, oh, I meant, yeah, SAS.
SAS, nice. So we have this SAS by the construction. Okay, so this is congruent by SAS. That's our construction. They are congruent, in particular, these 2 angles will have the same ratio and the same measure. This implies angle F equals angle AFG. But by our assumption, angle F is the same measure as angle B. This is the same as angle B. So from this, we conclude these 2 angles. Okay, Isabel. Now we see these 2 angles have the same measure. What can you say about these 2 lines?
They're parallel.
They are parallel because the corresponding angles have same measure. The 2 lines must be parallel. This is the big step from our intercept theorem.
Question?
Yes.
Couldn't you just say angle B? Hold on. Yeah. BAC instead of angle B, because that makes it sound a lot more understandable.
Okay.
Because I didn't know how can you just give it correct.
Okay. So let me change this. Maybe it's better to write. You are absolutely correct. I will rewrite this part. This will be angle EFG.
Mm-hmm.
EFG is the same as ABC.
Mm-hmm.
So this ABC angle ABC. So this implies BC parallel. Okay. Now we can apply the intercept theorem. These two lines are parallel. These two triangles are similar. We just verified over there. Two lines parallel, two triangles similar. So by the intercept theorem, similar to now what we have checked this triangle is congruent to EFG, but it's also similar to ABC. If we combine the two, we see these two triangles are also similar. So we have this condition and this condition. Combine them. Okay. This completes the proof of the theorem. Initially, to check that the two triangles are similar, we have to verify two sets of conditions. First set about angles and second set about sides. Now with this theorem, we only need to check the one set about the angles. If we can verify this, then the triangles are similar. We don't have to go check the sides. Okay. And the method that this is proved will be used again and again in the future to prove other similarity theorems. So given two triangles, the key step is to create a copy of this to show that these two triangles are congruent and these two triangles are similar, then this one will be similar to ABC. So we will have another proof in the same flavor, and this will get homework. You will give a proof of a similarity theorem using this approach. Okay, now I'm going to list the congruence theorems and the similarity theorems. Aaron, no. Congruence theorems and similarity theorems. we have this ASA congruence. We have this SAS congruence theorem. And we have the SSS congruence theorem. And we have the corresponding theorems for similar triangles. SAS similarity. This time we don't have S, just AA similarity. SAS similarity theorem. And this SSS. In certain sense, this AA similarity theorem is derived from this one. Even though we stated three pair of angles, we only need to check two of them because the third one followed from the interior angle theorem. And let's compare the SAS theorem with SAS similarity theorem. Let's get some space. Oops. Okay, so ASA, if we have two pair of angles, then the two triangles are congruent. The SAS similarity theorem, we have two pair of angle, the sides, AB over EF. They don't have to be the same, but the ratio. You can see the similarity and the difference between the two theorems. One for congruence of two triangles. The sides must be the same. One for similarity theorem. They don't have to be the same, but the ratio must be the same. We also have the SSS theorem. If we have we conclude the two triangles are similar, congruent, sorry. E, F, G. The SSS similarity theorem the ratios. The two triangles are similar. Okay. Again, I put them side by side for easy comparison. If the ratio is 1, we go back to the congruence theorem. For general ratios, we have the similarity theorem. And so how to prove this similarity theorem? We will use the congruence theorem and combine it with the intercept theorem. Okay, let me show how this works. So the bridge between these two sides is the intercept theorem. So this theorem helps us to go over from the congruence to similarity. Okay. Okay, so let's have 5 minutes break. After the break, I will show you how to prove the SSS similarity theorem using the congruence theorem and the intercept theorem. In this week's homework, I will ask you to show the similarity theorem using the congruence theorem. Okay, 5 minutes break, be back at 23. How to prove using the congruence theorem. The intercept theorem. Okay, so let's draw two triangles, and we will show that they are similar under some conditions. A, B, C. And the assumptions is, so in the assumption for the SSS similarity theorem, we assume the corresponding sides have the same ratio. That will be our assumption. We wanted to check, but we haven't done yet. Okay, now let's recall to see that the two triangles are similar. What we need? What are the conditions we need to check to conclude the two triangles are similar? And what is missing? Okay, Amy, what's missing here?
Um, uh,
Let's go back to the definition of similar triangles. First part, second part.
you need the angles.
Okay, the angles condition are completely missing. We need to check if we can. So what we need angles. Oh, here's the last word. That's not easy. We have no connection between the two. Why do they have the same measure? Why do they have the same measure? No idea at all. Okay, so but we do have the congruence theorem, the intercept theorem. Let's see what we can get from this condition. Okay, so I will start from point A. On this side, I find a point whose length is the same as EF. That's what we have done before. Okay, step one, find. Okay, this can be done. Let's find a point here. Similarly, we find G hat. Can be done. Place it here. Okay, connect.
Question.
Yes.
Could you write A/E? Because like I see that's a possible way to write this.
What's that? I'll try it again.
I think you could write A/E, I think.
Okay, let's be better because the two. Okay. Oh, sorry. Okay. Yes, it can be done. So we can move this point to anywhere. We move it to here, and we find a point with the same length. We find a point with the same length. Okay. Connect. Okay, nothing special, just connection. Okay. Now we have to check these two triangles are similar. These two triangles are congruent. If we can do these two steps, then these two will be similar. Okay, so the idea if we can verify these two properties, then the two triangles will be similar. Okay, this will give us what we want. Okay, we will check them one by one. One by one. These two triangles. How do we check that they are similar? I will start with this one. 2, 1. I check this one first. Okay. What do we know about this ratio and this ratio? Are they the same? Okay, Kira, you said yes. What's the argument for this?
Basically, like, since supposedly F, like the copy of F to A and then equals like F to E, and then the copy of G to A is F to G is E to G, and then we said that AB over EF equals AC over EG, so technically the ratios are the same.
Okay, so in this equality, I can replace EF with AF, and replace EG with AG. Let's see what we get. I'm going to copy this one first, then do the replacement. I will copy AB over EF equals AC over EG. I just copied. Then by our construction, this AEF can be replaced by AF. This EG can be replaced by AG. In particular, these two ratios are the same. Okay, Isabel, now we have the ratio. Could we conclude the two triangles are similar and why?
We can, since like the ratios are the same, meaning that like they're like kind of like similar. Like I don't know
What's
how
the
to
theorem?
um
Which theorem? The intercept theorem. Maybe the converse of intercept theorem. Same ratio imply parallel. Parallel implies similar.
mhm.
Okay, very good. So this implies FG parallel to BC. This implies, so this is the intercept theorem. This implies the two triangles are similar. Okay, now we move to the second part. Are these two triangles congruent? Okay, so we want to apply the SSS congruence theorem. By our construction, we have one pair, second pair, they are the same by construction. What about the third pair? Do they have the similarity? Why? Okay, think about this. This pair done. This pair done by the construction. What's missing? Okay, so the second step, we need to check the missing condition. Okay, how to verify this? Aaron, any thought?
Write this down.
And Fred, what do you think? We want to use this SSS congruent theorem. We need to check all sides. We know the first pair.
Can you hear me?
Then, yes, Fred.
Here, right?
Aaron, and progress, Aaron, still working? Amy, progress?
No.
Why do they have the same length? Okay, so we have used one condition already, but we haven't used this part yet. How do we use this? It does have FG.
Yeah. Wait,
Okay, Aaron.
isn't that what the F and the G are too?
Okay, so the key point is again the intercept theorem. Intercept theorem not only tell us they are parallel, but also the ratio of the two is the same as the ratio of these two. Okay, another conclusion of the intercept theorem. Not only the parallel, but the ratio is the same as and AG by our construction is the same as EG. Then EG and AC has the same ratio as FG over BC. So this is our condition. Okay, so this step is the intercept theorem. And this step is our construction. AGEG. And this step is our assumption. Okay, so each step we use something that we already have. Now we have the two ratios are the same over the same denominator. The two ratios are the same. The denominator are the same. The numerator must be the same. Now we conclude. All right, we have the third pair and the final pair of sides with equal lengths. These two by construction. Now we can apply the SSS theorem. Conclude the two triangles are congruent. So by the SSS theorem, the two triangles are congruent. Okay, now they are congruent. They are similar. So we finished this. We can see these two triangles are similar. through this bridge. Okay, so you can see how did we prove this AASSS similarity theorem? We used the thing that we know we had proved before, the congruence theorem and the intercept theorem. So in this week's homework, as I mentioned before, I will ask you to finish this bridge. From here to there, go over the bridge. Okay, any question about this? Then we will move on. Okay, so next, let's consider right triangles. This is a very special class of triangles. One of the angle is 90 degree. So we call this the right triangle. And a property about the right triangle is the Pythagorean theorem. We call this side smaller c, A, B. Okay, two special cases. The first one, oops, missed it too much. A, B, C. If this side has length 1, 45 degrees, right angle. Okay, Aaron, what's the angle B?
Hold up.
Could we find angle B using the information here?
C equals 90. Okay, so B is, let's see, also 45.
How do you get that?
Well, let's see, A squared plus B squared plus C squared, right? Wait, no, wait, hold on, wait, no, something's wrong.
The interior angle theorem, because the total is 180. Okay, so now the two angles have the same measure. What can you say about the two sides, AC and BC? Amy.
They're equal.
Okay, equal length. This implies, so since angle A, angle B same measure, AC equals BC. But we know AB equals 1. So AB equals 1. So 1 is also AB squared. By the Pythagorean theorem, that will be AC squared BC squared. These two are the same, twice of AC squared. So AC squared is 1/2 AC. Simplify this, we get okay. So for this particular right triangle, we can find the sides. Okay, let's check another special right triangle. Call this A, B, C. Again, right angle, this time 60 degree. Okay, Kira, what's angle B?
Wait. 30.
30. Okay. Okay, now if we assume AB is length 1, could we find AC and BC? Some of you know the results. Amy, maybe do you know that this length?
No.
Okay, Isabel, have you seen this before? Maybe you know the result.
I think I've seen it before.
Okay, so the result, this will be 1/2. This will be, and we want to see why. Okay, to check this, I will find the midpoint of AB. I call this D. I connect the CD. Okay, let's All right. Midpoint. Okay. If we apply the midpoint theorem, what can we say about the two lines? Aaron? And Amy? Two midpoints. What does the midpoint theorem tell us?
That DE and AC have to be parallel.
Nice. So they must be parallel. So by the midpoint theorem. Or more general, the intercept theorem. But the midpoint is good enough. So DE parallel to AC. In particular, the two angles, angle BED is 90-degree angle CED. Okay, so these two triangles, let's check the two triangles. Triangle BED, triangle CED. I claim they are congruent. Let's see what theorem would we apply here. Okay, two angles, both 90 degrees. We have a pair of angles, and E is the midpoint. These two sides, same length, and they share a common side. Okay, what theorem could we apply here? Aaron, what's that theorem?
We could apply we could do SAS because we know B E equals EC and there's a 90-degree angle.
So this will be SAS. So by the SAS theorem. Okay, now what do we know? So this also implies the corresponding side. I pick BD. The corresponding side will be CD. Okay. So, and the corresponding angles, angle B, C, B, D, angle, maybe EBD is better. EBD, ECD. EBD by our previous step, we know this is 30. So this turns out to be 30. So what's left? Angle ACD. 90 subtract 30. 60. Okay, so this is what's left. Okay, so this triangle ACD, two of the angles are 60. This one is also 60. So this is a equilateral triangle. Triangle A which implies AC and AD are the same. But we just claimed AD D is the midpoint, so AD is half of AB. AD is half of AB. So AB is 1, this is 1/2. In this way, we find AC. Now we can use the Pythagorean theorem to find the BC. That's how we find the length of the two sides of the right triangle with angle 60. Not easy. Okay, so these two special cases, more generally, we're not that lucky. We don't have exact numbers, but we use the trigonometric functions. Sine theta, cosine theta. Two most popular trig functions. Okay, we'll start with the right triangle. Because this side is 1, if this side is theta, then the length of the side facing the angle theta will be sine theta. The length of the side adjacent to the angle theta will be cosine theta.
Oh, that's what I was gonna say. Sorry.
Okay, so now let's reformulate our result before. If theta is 45 degrees, Kira, you have a question?
Does it matter which like side adjacent to theta it is?
It's very important. It's very important. Okay, so the side facing theta, we call it a sine. The side adjacent to theta, we call it a cosine. This is very
Does it
important.
always have to be the like the base adjacent to
No,
theta?
no, you don't have to. For example, we may call this alpha. Then this side will be sine alpha. This will be cosine alpha. So always, if we call this angle, the side facing the angle will be sine. This alpha will be sine alpha. Okay, so our previous calculation, 45 degrees. The square root of 2, square root over 2, we have the calculation. $60. If we go back to there, the side facing the angle is square root of 3 over 2. The side adjacent to it is 1/2. Okay, so we reformulated our calculation using this trigonometric functions, and we will learn more about them next time. We'll stop here for this lecture. Any questions?
Is there gonna be class next week?